Hello and good afternoon, everyone, and welcome to another session of the CODA webinar series all about decommissioning. My name is Rianne Gilbert. I am the General Manager here at CODA, and today we're hosting a very unique webinar in collaboration with our CODA partner SICA, which stands for the Subsea Innovation Cluster Australia. We'll be hearing from a number of SICA members presenting their decommissioning technologies with a focus on innovation. Think of it like speed dating. As we go through our presenters, please do pop your questions in the chat and we'll get to them at the end during our Q&A session. Please be clear as to which company or speaker your question is directed. Today, I'd like to start by introducing Dr. Colin McIver, who is the Cluster Manager for SICA, and he will provide a short intro to the webinar. After you'll hear from me regarding our first presenter. So without further ado and delay, please, Dr. Colin McIver.
Thank you for that, Rianne. SICA, Subsea Innovation Cluster Australia. We are the national industry-led cluster that connects the ecosystem that is Australia's subsea and underwater sector. And we connect across energy, defence, renewables, and we bring together operators, suppliers, researchers, and government with our main aim is to accelerate innovation and build and promote local capability. So today's session is really about showcasing some of the new and innovative technology that have been developed by a number of SICA members that has direct application to decommissioning. And the intent of this is to, I guess, in a relatively short period of time, get you all up to speed with what is out there and give you enough information. Not that you can run away and copy everybody's idea, but that you can ask dangerous questions at the end. So this is a great opportunity for SICA members, and thank you to CODA and Rianne. So Rianne, I'll hand back to you.
So I'd like to start with our first speaker for this afternoon, Robert Spencer from ALARP Solutions, who will be presenting on their intelligent compliance tool for petroleum legislation. So Robbie, please take it away.
So firstly, thanks to CODA and SICA for having us today. I'm going to start by getting you to imagine this scenario. So you're trying to answer a regulatory question across 9 different pieces of legislation, multiple regulatory bodies with no single source of truth. How do you know where to look? How do you know what applies? And when you finally get to an answer, how do you know that it's correct? I'm guessing many of you in this room didn't have to imagine very hard. You've all been through this before, if not hundreds of times. Every compliance tool currently on the market gives you an answer. What none of them give you is proof that the answer is correct. When it comes to compliance, that distinction matters enormously. One wrong jurisdictional call can burn between $2 and $7 million in vessel standing time alone. A fault-based breach can expose a body corporate to up to $3.3 million per offence, and that's before the daily continuing penalties start to stack up. So what if the regulatory question only took minutes instead of weeks? PetroLex is an expert system that takes your legislative queries and outputs a traceable, verified response in seconds. That could save up to $3 million per delayed answer. And thanks to the recent report from CODA, we all understand why that matters at scale. The decommissioning sector is carrying $43.6 billion of liability, so those savings compound significantly. Just go to the next slide. Awesome. So I'm going to play a video that includes a live demonstration of PetroLex working through a real encoded scenario. This one's of a disconnectable FPSO navigating its transitional phases. Hopefully that's playing. Yeah, cool. So first and foremost, the legislation is encoded, not just indexed. This is the foundation of how PetroLex works, and it's what sets it apart from every search-based tool or AI on the market. We're not doing a keyword search over PDFs. The logical structure of each provision, the conditions, the obligations, the exceptions, and the cross-references are all captured in a form that mirrors the original text. Secondly, PetroLex reasons across instruments simultaneously. It doesn't evaluate one document at a time and stitch the answers together afterwards. In this scenario, the OPGGS Act, the Navigation Act, and the safety regulations all intersect. PetroLex evaluates the intersections together in a single query. That means when, for example, the facility status changes and jurisdiction shifts from NOPSEMA to AMSA, PetroLex can catch that transition in real time and highlight any conflicts. Thirdly, every verdict shows it's working. You'll see in the video that the output doesn't just give you a yes or no. It gives you one of 7 verdict states mapped directly to how regulatory obligations work in practice. And then every verdict state shows exactly which sections apply, which facts triggered them, and the reasoning chain that got you there. The key differentiator, formal verification. This is where PetroLex is genuinely unlike anything else in this space. Most tools will sample test a handful of scenarios and extrapolate. A provision with 12 input fields has 4,096 possible combinations of facts. PetroLex runs a mathematical proof across every single one. Not we tested the likely causes and made a best guess. It's we tested all of them, 0 gaps. That's the difference between an answer and a proof. And in regulatory environment where getting it wrong has the consequences I talked about in the first slide, that's exactly what you need to solve your problems with confidence. I'll just flick to the third and final slide. Hopefully I am well within time. There's 3 numbers on screen. I'll keep this brief. So $500,000 to $3 million saved for each question resolved faster. That's avoided standing time, grounded in offshore vessel day rates. When a jurisdictional question moves from weeks to minutes, the vessel doesn't sit. That's what PetroLex solves. 40 to 60% reduction in external legal spend on regulatory mapping. PetroLex shifts the legal effort from what does the law say to what should we do about it. That's a significant reallocation of some of the most expensive time on any project. And again, just to reiterate my first point, $43.6 billion in national decommissioning liability to 2070. 700 wells, 7,600 kilometers of pipeline, 520 subsea structures. Efficiency gains don't stay marginal across that pipeline. They compound. So what I've showed you today is just one scenario, the FPSO disconnection. We've also built a trailing liability and WAMP life cycle that's encoded and been formally verified. But the real potential of PetroLex goes well beyond decommissioning. Having the ability to input any legislation related to any project anywhere in the world where multiple legislation and regulations intersect will allow you to save time and money. And just like PetroLex, I will finish early, give you some time back, and thank you very much.
Thank you so much, Robbie. As a regulatory specialist, I see so many applications for your tool already, so thank you for that. And thank you for sticking to the time. So next, we're going to hear from Mark DeCastro from TMT, who will be introducing a range of tools from TMT. So Mark, if you'd like to start, please do.
So thank you to CODA and to SICA for the opportunity. Francis, Rian, Colin, Danny. It's always good to have these opportunities to share some of the experiences we've had. I'm going to be talking about 3 tools in particular that we've developed over the years. They're not new tools, however, they have evolved to stay current over the years. And with that, let me get straight into it. So the first tool I'm going to talk about is a subsea top drive. We operate in a space of rigless decommissioning, so most of these tools are operated from vessels of opportunity. Usually when we operate from a vessel of opportunity, you don't have a derrick with a tower, and so you're unable to apply any torque in the same way that a rig can. And there are some operations that require this. So this tool is designed for removing tubing hangers and internal tree caps. And to do that, you need to land out on top of a tree or a wellhead, usually at a horizontal tree, and latch onto a tubing hanger. And to do that, there is usually an interface, and there's some rotation required to unlatch the tubing hanger or the internal tree cap. And then there is a vertical movement required. Sometimes it can be quite significant, particularly if it's an old tree, and when we're talking decommissioning, you may have damaged lock rings. A rig can typically pull with a very high force, and so we've built in a number of hydraulic cylinders that can extract with up to 300 tons. So this tool is it's deployed on wire. It can apply a torque around about 10 kilonewton meters, which is usually more than enough to unlatch a tree cap or a tubing hanger. And then, as I said, we can pull with somewhere between 300 and 350 tons. The interesting thing is when we pull entirely vertically. There's no risk of pulling at an angle. So the results of the extraction are normally more successful than those done on drill pipe. And we found that this has been vindicated by the very low forces that we've actually required to remove these tools. It can be operated on a downline through an AWACS or with an ROV. It is in fact field proven, and I think this is really important. Everything I'm showing here isn't vaporware. It's stuff that we've operated. It was designed here, it was built here, and it's operated by people here. There we see it offshore and in the yard. So that was that tool. Sorry for the time limits. I'm going to try and keep within the time. The cement injection tool is another one that we've had for some time. We haven't used for a while. We'd love people to know more about it, hence bringing it in here. And what this tool does is it puts environmental cement plugs into a B annulus. So we look at a typical well schematic here. The tubing has been removed. So this 9 5/8 bore is effectively now the A, and the B is between the 9 5/8 and the 13-inch. And why do we need to put a barrier there? Because when we cut this wellhead, we're going to remove an existing barrier, which is the seal assembly between the 9 5/8 and the housing. So that environmental barrier needs to be reinstated so that we don't contaminate the plug that we've installed during P&A. This is a standard product, but it is fully customizable. So when we look at it in the picture in the schematic on the right, it's quite compressed vertically. So these packers, these inflatable packers, are the two black lines over here. And the distance between the two, the upper CIT, as we call this one, and the lower CIT, is the length of the cement plug that you're going to install, which is usually around about 100 feet. Again, field proven. There it is. Not a great picture, but you can see it offshore. This was in the Timor Sea some years ago. Again, if there's questions, I'll go into them. All I'm trying to do here is present some really interesting concepts of tools that people might not realize are available to them. Here's a video showing an assembly going into a well. And we see the upper and the lower. There's a land-out plate. The land-out plate with a wire stinger ensures that we position the tools at the right depth. So the higher one might be 10 meters below mud line, and the lower one might be 30 or 40. Once we've landed out, we inflate these packers to create a seal. And then we're going to punch using these mechanical hydraulic punches through the 9 5/8 casing into the B annulus, and any trap pressure that is there is going to get vented back through these two hoses, which we come and are routed back to surface. And we ensure obviously that there is no live annulus, and once we know that, we move on to the lower CIT and we do the same process there. We extend the punches and we punch into the lower section of the B annulus. So we now have a circulation path between the two punch locations. We confirm that path by pumping water down through a 1-inch hose, which goes through the first one, into the second one, into the annulus, back through the case, the punch, and up through the second hose back to surface. So we know we've got a circulation path. We can now pump cement, and we chase that cement down with a high viscosity plug, so we know we've got exactly the right volume. We stop when we've pumped the right volume, and hydraulically we unlatch the upper CIT from the lower CIT, and we're then able to remove the upper CIT. The lower one remains there. It's sacrificial, and it's a platform that supports this plug in the 9 5/8. And then we can recover the upper all the way back to surface. And there we have all our barriers reinstated. It's when we say the B annulus is the one that requires it, it's because the 9 5/8 goes down to a depth of typically 2,000 meters. And that's why we need to address that annulus. So that's the cement injection tool. Next up, and the last one, which is probably more familiar, is the AXE wellhead severance system. Very proud of our record that we haven't left a wellhead behind in over 100 cuts in 25 years. There we see two interesting cuts. One of them on the right, very early one, where we had some centralizing fins, which meant that we had to cut through up to about 6 inches of steel in some cases. And on the left, there was a surprise in that we were cutting through a coupling, which the client didn't realize was there, but in both cases didn't cause a problem. We were able to cut. This tool, again, locally developed, locally maintained, locally operated. The people who maintain the tool are the people who go offshore with the tool. On the right, we see a picture there of some hyperbaric testing. So a hyperbaric chamber was built so that the unit can get tested under real life conditions. And on the left, we see the full team there on one of the more recent campaigns. We have a process of ongoing improvements. Over the 25 years, there have been multiple process and technology improvements built into the system. We now have, full camera monitoring systems everywhere, so the operators never have to go near any high pressure environments. We have digital displays, we have data recorders, so everything is logged, and this ensures that the information and the experience we gain is never lost and is continually applied to future projects. And then a key aspect again, which is really important to us, is that the equipment is here. We keep it warm stacked. We test it every 3 months, and it's ready to go. These are photos that were taken from recent mobilizations, but this is what it looks like in our yard a couple of months ago. So that's the axe cutting system. I think that's it for the tools. Just on closing, I guess what we try and emphasize is, because we're local and we have real people, we have real equipment. It's not vaporware, it's not ideas, it's not a banding together of a bunch of contractors. We've got real experience out there in the field over a long period of time. And importantly, we are here and it's now. So that's us. I think I've just come in at 9.5 minutes.
Oh, you
Thank
did.
you.
You did well, Mark. Thank you so much. It's really great to see locally developed and operated tools. So thank you very much for that.
That's
We're
a
going to
pleasure.
move on, but I'm sure there will be questions for you. So next we have Doug Cleland from IQIP, who will talk to us about their internal lifting tools specifically for the decommissioning market. So go ahead, Doug.
Thank you, Rian, and thank you, Colin, and thank you for the invitation to speak today. Also, by way of introduction, IQIP designs, engineers, and delivers decommissioning-specific internal lifting tools, specifically for heavy lift removal of jacket and topside structures offshore. Removing these structures that have been in place for many years and often decades requires real dedicated lifting equipment and execution methodology to remove these structures both safely and efficiently. And removal of such assets involves much more than a reverse installation approach, and there are many variables to be considered and engineered up front to ensure a successful and safe removal campaign. In the engineering phase, really a clear understanding of the structure geometry that needs to be lifted out is needed, including the internal profile of the structure, including material grade and any internal obstructions, but also for the surrounding structure, including adjacent beams and bracing. Further considerations also need to know the cut profile that we need to work around. Commonly, this includes a castellation cut that separates the topside from the jacket, and we need to also know the horizontal and angled cut lines affecting the internal lifting tool interface. In this engineering phase, we conduct extensive modeling and structural analysis, and it's critical to identify the localized stresses in the lifting cans or the jacket leg or the pile, and also the internal lifting tool itself. And these must all be within accepted limits and certified norms. Further modeling is done to confirm the structural integrity of the internal lifting tool itself, considering the numerous and various load factors acting upon the tools. Some additional risk areas are identified, typically engineered out with modified internal lifting tool geometry, but also by modified gripping or contact area, and the overall tool geometry and actuation method can also be optimized depending on the offshore sequence, the installation vessel, and the overall operation. Really, the collaboration between ourselves and the heavy lift contractor is essential to determine the interface between these internal lifting tools and the vessel and the crane itself. What this results in is determination of the number of tools to be used, also the spreader frame design that can lift and handle the internal lifting tools, and also whether shackles or link plates, as you see on the screen in this particular example, might be better suited for the lift that needs to be done. One of the key aspects to ensure the safe and efficient lifting of structures such as these, because we can be lifting structures that can be, say 2, 3, even 4,000 tons per piece. So we can really use a small number of tools to lift very heavy structures. As you can appreciate, around the world, there's lots of different structures and different water depths that have different designs, and ultimately these will require different internal lifting tool adaptations. So there is indeed standard portfolio equipment that exists within certain diameter and working load limit ranges, but often custom-built internal lifting tools are needed to suit the internal project and the specifics of that. Fail-safe lifting is a non-negotiable. Losing contact or letting go of a structure offshore simply cannot happen. In the event of any hydraulic failure, the gripping capacity of the internal lifting tools, or the axial capacity of the internal lifting tools, is increased, so eliminating the risk of losing or dropping the structure. The internal body of the ILT itself has a tapered profile, and when hydraulically actuated, the tapered body extends vertically, and this pushes the gripping teeth out to the inside of the jacket leg or pile wall. As mentioned, in the event of any hydraulic failure, which is extremely unlikely, but the axial load will increase rather than decrease. So often one of the first questions that we get in case of any failure. So it's patented technology and has been the benchmark for, the underlying principle of this fail-safe design has been the benchmark for installing and removing structures for 2 decades already. And although these tools are can be very high capacity and customized specifically to offshore decommissioning, they have been used extensively in other areas. However, in Australia, as we're really approaching the big liability of the decommissioning market, then this is a good potentially entry for this kind of equipment. Within the design of the equipment, there are additional measures engineered into the design to ensure these tools are correctly engaged and functioning to the correct specification, or the nameplate specification. And this provides also several levels of contingency and verification of function in the field. And then lastly, what I'd say here is this equipment, as you can see, there's a spreader frame arrangement, there's lots of different rigging setups. The jacket, the top side has been separated from the jacket, so you can see it's a very elaborate engineering exercise to get to this position. However, we've completed more than 50 projects around the world, decommissioning projects, specifically with heavy lift contractors, to name but a few, the likes of Herema, Skoldis, PetroLex, Saipem, and Allseas. Each project and structure really must be considered on its own individual merits, and we can't emphasize enough that sufficient time and focus must be addressed very early in the project stage, in the engineering stage, to ensure that a successfully engineered lift or removal can happen seamlessly. And ultimately, for an overriding objective for IQIP in the design and supply of this type of equipment, for removal projects, we're aiming to reduce the number of lifts to remove these heavy offshore structures, contributing to fewer operations, fewer vessel days, and an associated reduction in cumulative risk. And that is the end of my slides. Thank you.
Great. Thank you so much, Doug. I have questions regarding marine growth weight, but I'm going to wait my turn like everyone else and ask you a bit later. So for those of you who have just joined us, please do pop your questions there in the chat. We'll get to them after the last speaker. So number 4 on the agenda today is Simon Renwick, the founder and CEO of WaveX, who will be presenting on harnessing wave energy and how it can assist in the decommissioning industry. So Simon, it's over to you.
So hi there. Yeah, my name's Simon Renwick. I'm from a company called WaveX. And we're building a power platform that's located in strategic and high-value marine settings and that never needs refueling. We enable operators of marine and coastal infrastructure like yourselves to reduce power costs and OPEX and enhance capability through the deployment of our IP. Key to this discussion is the word platform in both the figurative and the literal sense of the word. Physically, we're a 1,000-ton floating steel platform that uses semi-submersible technology to make the corners of the platform resonate up and down like a piston, which then self-react against the rest of the structure to generate electricity. Figuratively, it's a platform technology. It can be used across a wide range of marine applications, like things like defence and utility power, to deliver electricity to places where there's never been electricity delivered before. But especially in an oil and gas and a decommissioning setting is this applicable. The wave energy component of the platform is vitally important. Ocean waves are one of the most concentrated forms of renewable energy, 10 times that of solar, 5 times that of wind. So to deliver the same amount of power from a diffuse resource like solar, for example, that would require a platform many times larger and an order of magnitude more expensive than what you see here. So creating electricity from the medium in which we're surrounded is the key enabler for persistent concentrated power that makes economic sense. In terms of oil and gas and decommissioning applications, the WaveX system is designed to be autonomous, it's unmanned, and has minimal planned maintenance and never needs to be refueled, removing the logistics and HSE burden and the associated operating costs reduction. We offer megawatts, not kilowatts, a key differentiator, powered by ocean waves, firmed with batteries, and all sitting topsides rather than subsea, allowing a wide range of potential use cases. Having the biggest payload and deck space of any competitor, it allows us to provide power to recharge drones and AUVs, but also power for edge compute. The case for edge compute in offshore oil and gas and decommissioning has recently been proven by our partner WinDC and Armada in the States, who deployed their modular data center directly on an offshore drilling rig in Norway for Aker BP, enabling local processing of operational data independent of shore connectivity. This was followed by a deployment with Aramco to power AI-driven safety monitoring and real-time decision-making across offshore energy facilities. The next step, as we see it, is for standalone edge compute with an autonomous power supply, and that's what we're doing here. So we know we have particular application for oil and gas and decommissioning, some of which are subsea monitoring, providing cost-effective power to platforms while decisions around asset decommissioning are being taken, and even field developments with our platform that has a low-cost decommissioning scenario attached to it, where we can repurpose our power platform at the end of field life. But I'm not actually here to tell you what to use our platform for. We're at this beautiful stage in our business where we recognise that you guys out there at SICA and CODA are the experts. The world of AI and autonomy and sovereign capability is moving so quickly. We'd love to hear from you directly about how you can see a use case for our platform for your specific offshore decommissioning application. Many of you will know our pilot project in Albany, where we're planning for first electricity in Q4 this year. We're looking for partners in the oil and gas and decommissioning space who'd like to demonstrate a future capability at pilot scale with us and secure the advantage of being an early adopter of our technology. We're a power source for oil and gas and decommissioning located in strategic and high-value marine locations. We can house the widest array of third-party equipment on the largest deck powered by the most capacity and all maintained above the water, not in water or underwater moving parts. We'd love to discuss potential use cases with the members of SICA and CODA for specific applications in oil and gas, especially as it applies to your vision for the future of decommissioning. Thanks.
Thank you so much, Simon. I'm smiling because, as you know, I'm a big fan of your technology, but we'll move on, and no doubt there will be questions later. So, and last but certainly not least, we'll hear from Louise Bruce from BMT, who will be introducing DEEP, which is a digital platform that orchestrates disparate data, models, and tools across the full decommissioning lifecycle. So let's hear from you, Louise.
Thank you so much. That was a really great segue from that presentation. Thanks, Simon, and thanks to SICA and CODA for inviting us to speak today. Before I start, just want to acknowledge my co-authors of this presentation. Damien Richards is my partner in crime in the APAC region in terms of bringing their technology through to those who would like to get involved. But also Soma Maraju, who hails from the US, and he's the architect behind the development of this technology, and also leads the development team as well. So I don't really need to spend too much time discussing what the challenges are for the decommissioning industry. As Simon said, you guys in the audience, members of SICA and members of CODA, are the ones who know more about what's going on in the decommissioning world, certainly, than I am. But just to sort of briefly, start with where we are, we've got a big, huge wave of decommissioning on our shores. I'll be using a few intentional puns as we go through this presentation. So decommissioning is very complex. There's hundreds of wells, lots of regulations. We heard about that in our first presentation. And we've also got something close to my heart, which is the environmental considerations and those expectations about how we leave the space that we work in such a way which is environmentally sustainable, is increasing in terms of its requirements. So the journey through the decommissioning process is a decision-heavy journey. So even right from the start, there's major decisions that need to be made, and those hundreds of decisions that get made are all interlinked. So if you think of right at the start, those upfront, do I stay or do I go? Apologies, I've had that song in my head for a while now, but if we stay, there's trouble. If we go, there's double. Do we remove everything? Do we do a partial removal? Or do we do some sort of in situ decommissioning somewhere in between? So what is the optimal timing? Do we act now? Do we wait a while? There are so many decisions that need to be made right at the start. What is the condition of our asset? There's a lot of that at the beginning. Then when we actually start to execute, there's all those questions about what's the weather look like before we get out there? What are our vessel availability? What is our resources we got? How do we balance, and this is the really tricky one, the cost in terms of the decommissioning project with safety, which is something that we cannot compromise on, the environmental risks, and also getting that regulatory confidence, which is really important too. How do we map that plan out? And then once we've made those big major decisions, there's thousands of small decisions. You need to pick that safe weather window. You need to have that critical where you're going to do your lifts and the plugging of those wells. You've got to organise all those vessel logistics and sequencing. And the thing about it is you've got to not just have your plan, but you've got to have a plan which is adjustable. You've got to be proactive, and you've also got to be reactive, and you've got to make lots of decisions. If anyone, and most of you out there probably have been in this place, ever worked out on a deep an off-shelf structure, know how challenging that environment is. So those are the things that you need to constantly evolve in terms of your planning. So how do we do something where the information is often scattered and the expertise and the people who know the answers to those questions are across different disciplines? So one team, for example, might have the met-ocean and the weather intelligence. Another team knows all about the structural engineering constraints. Another team might be the one that is doing all the monitoring, looking out for the whales, for example, the environmental impacts. Then you've got a huge team of finance people who are making sure that our costs and our schedules and our budgets and our project management are working together. So if those decisions are made in isolated silos, you're missing that chance to keep speaking to each other. And that is that missed interaction. So, for example, a weather decision might not factor in a constraint in terms of a vessel availability. Also, as I said, last minute changes, if you don't put that into those equations, you can get those nasty surprises during the execution of your decommissioning project. So what is the question? How do we coordinate all these decisions into one systematic, integrated way? How do we make sure every decision is based on the right data at the right time so that we can plan effectively and execute optimally? And how do we confidently demonstrate that we've got it right at the end? In other words, how do we bring clarity into this complexity? So where are we? Here is a technology that I've been working with since it was introduced to me almost sort of 8-9 years ago now. It's been around for about 15 to 20 years. It was developed for the offshore oil and gas industry for operational and asset management. It is an integrated decision platform. It has that if you think of that one-stop shop, that one digital thread that runs through all of those operations. So in terms of how that works in a decommissioning sense, it works as one digital thread that runs through from the planning stage, the approval stage, the execution, and also that monitoring once you've completed your decommissioning project. It's connecting all those data and the models into that one space. So where do we start from? So that's the top part. That's the life cycle of your decommissioning project. The next part is for each one of those stages, you've got those parts. So first of all, you collect the data, and that's the bit that I have the most admiration for, because the amount of data that needs to be collected to help make those decisions is huge. That's the big part. Then you have to then take those data and make sure you transmit that into a fast, efficient way, and then to get to the places where your operators need that information. Storing it, so that's storing it and organising it. It's what's important there is not just about putting it into a box and putting it into a storage, but also making sure you've got the right governance, who owns what data is being used for different things, to make sure, crucially, that the data that's been used for one lot of decision making, for example, MedOcean, is used the same data that's used for a different lot of decision making, so that we have that standard communication there, as well as that audit trail too, when it comes to making those decisions. The bit that I love to jump into is the analyze. So that's all the modelling stuff. By trade, I'm a modeller, ecosystem response modeller, but I love any kind of models. I've also worked in process modelling and control as well in a past life. So that's when you can take all the data that you've collected and stored and governed and do those what-if scenarios. And what I love about this is you've got that virtual ecosystem, digital twin situation where you can just keep doing different possibilities and explore different possibilities until you get the optimal possibility without having to spend all that money in doing those testings. And then finally, what you need in the end is a way in which you can, so people like myself who love doing all those analytics and love putting all those pieces of the puzzle together, it's then about how do you visualize that and how do you provide those insights into those decision makers, and that's where you finish the dashboard at the end. So where in terms of that life cycle, planning, approval, execution and monitoring, what I just want to finish with in terms of describing the technology here, and please come back to me at any stage with more questions, because this is a very complex, to match the complexity of decommissioning, this is a very complex product that I'm going through here. But there's three things that I really love about this product. The first one is those dashboards, and the fact that it can do something from so the same data, MedOcean data, can be used in terms of your planning and scheduling, it can be used in your environmental considerations, but also in your monitoring and structural. The bit in the middle there, got a couple of dashboards there as the Analytics Studio. So the data that is stored in Deep can be then analysed by the people who are working in that space, so those customers can do those analytics. And again, going back to that decision support. So the main three things there are the fact that we've got a product that has been developed by offshore experts. So people who have worked on these offshore platforms, understand what is the requirements on there, have developed the technology that goes behind Deep. Secondly, it's the speed with which those decisions, so a lot of the applications that Deep is currently used for is doing the response to hurricanes in the Gulf, because it's really important when a hurricane's being tracked that you can make those quick decisions fast. And so the data speed with which it comes through, stores, and then gets analysed is really important. And finally, as I said, for me, it's all about the analytics, the ability to go in and actually start to ask those questions yourself. So that is the backbone in terms of the coordination of the technology. It's about getting that right information at the right time across that whole decommissioning journey. So finally, we've got a call to action similar to as Simon said. We've got a vision of a product that's been developed for offshore oil and gas operating. We want to turn that vision into something that is then taking our industry through that decommissioning journey. So we've got people, we've got experts across the subject matter experts across the maritime operations, design engineering, environmental scientists, we've got data analytics, we've got project management. We've got this core product that brings all those things together. We've also got the instrumentation in terms of the USVs that collect the data that goes through. We've got the building blocks, but what we're looking for is partnerships with the decommissioning community to really get this to a place where it is maximum value. So we need a project. So especially if it's at that first stage when we're looking at that initial planning, and that's how we can start. We're looking at people who are willing to join with us in that innovation collaboration space. That especially those who have a deep understanding of the decommissioning life cycle. We've got a lot of experience in the North Sea, but we don't have so much in Australia in terms of decommissioning. We've got that experience in terms of the assessment and risk prior to these journeys, and also some of the work that we've been doing, for example, in the offshore wind space. But it's looking for people who have more of that sort of lived experience there. We need to connect the different specific analytical tools. So we've got a few tools there that are already in deep, but we're looking for other tools that will be complementary to the tools that we already have. So again, it's bringing all those different analytics together with one set of data, but multiple decisions across different areas of expertise. We're also looking for a sponsor who can help to drive this innovation as well. So to finish, we've got deep. Deep is an ecosystem. It's not a finished product. We're not trying to pitch a shiny completed tool that's got all the bells and whistles. We're here to invite that collaboration. So we're actively inviting people to, with operators, service companies, researchers, technology providers, everyone who's listening to this webinar and those who might be watching it afterwards. We want you to come to us and work through DEEP as a collaboration integrated tool to help shape the next generation of integrated decommissioning tools. So your input, your expertise, and also partly your is this actually going to really work? So some of that sort of checking in to see what is actually going to work and what not. So if you just click on the QR code, it's a 2-minute a 2-minute form, just gives your name and your email and your ideas and feedback. So thank you very much again, and I'll hand it back over to Rianne for the questions.
Thank you so much, Louise. You know, such beautiful multidisciplinary complexity in the decommissioning field, and it's what we love about decommissioning, isn't it? So thank you all to all the speakers. We are now going to move on to the Q&A. So if I could get all the speakers to maybe reappear on the screen and show your faces, I will start with the Q&A. And I'm aware that some of these questions have been answered in the Q&A, but we're going to give you an opportunity to elaborate on them anyway. So I will start. Robbie, I believe this one is for you. Somebody wanted to know whether your tool could flag where regulatory bodies are contradicting each other.
Hey, Rianne. Yeah, I'm just going to introduce my colleague Jerry as well, who's got many years in the oil and gas industry. He's on the call with us. So it absolutely can, yes. So that's one of the key things we found with our FPSO disconnection, for example, where your safety case your field safety case is separate to your AMSA requirements. So although NOPSEMA have jurisdiction when it's a facility and that's within the field safety case, for example, it crosses over both boundaries in a lot of ways. Therefore, the best thing it does is it actually highlights where that problem is and allows you to dig deeper in more depth and understand how you resolve that, or whether you would need to go to the regulator to find out more.
Great. No, that's helpful. Thank you, Robert. Another question for you, Robert, or Jerry. What countries and/or global organizations are represented with their relevant legislation and regulations in the PetroLex database?
I'm not sure if Jerry can talk.
Jerry, would you like to make yourself visible and answer that one?
Thanks, Jerry.
Hi. Yeah, I've posted a quick response there. The tool is agnostic. You create digital twins of whatever statute you want. I believe the only condition is it must be in English, and then that digital twin, which is essentially is a word for word identical to the act or regulation or CODA standard, is then framed with logical operators, so that the tool can then interrogate all of the statutes that are loaded into the domain, and it will flag up inconsistencies. It will identify where things clash. And as I say, it's not limited. You can expand it to, I don't know, Brazil, if you can have a reliable translation of a Brazilian standard. The UK North Sea, obviously, it can accommodate anything.
Yeah, great. Thank you, Jerry. Mark from TMT, for the Australia seabed well decommissioning regulations, is there a definite requirement to cut and recover the subsea wellhead conductor, or is it allowed to be left in situ, seawater or depth dependent? I know you answered this, but it would be good if you could just answer it or maybe elaborate.
Yeah, it's an interesting one. The base rule, and I just had a quick glance at NOPSEMA's regulations, they say the base case is remove everything. The seabed is to be left as found, which means cutting below. But that's not to say exemptions are never granted. You know, in a typical case is when cutting, they have sometimes found obstructions in the well around about seabed level or just below, so they couldn't get a tool in to cut, so they accepted a cut at seabed level instead of 3 meters below. In other cases, operators have put forward compelling cases as to why there may be benefits to leave certain pieces of items or subsea assets in place, and NOPSEMA considers those on a case-by-case basis.
Yeah, that's what my understanding as well. Mark, there's another one here. Was the SSTD, which I think is the subsea top drive in my ever knowledge, ever used in Australia? And if so, what savings did it provide compared to using a semi-rig?
Yes, it was used in the Timor Sea in a full field P&A and decommissioning campaign that we did some years ago. And it resulted in significant savings, because whilst today we do see a number of LWI or light well intervention applications where it's a hybrid case in the field, and certain parts of the P&A are done by a monohull vessel with a riserless configuration, and other parts are done by the rig. And we assess these case by case, and if we can do it the full field riserless, we do that, and we've done that on a number of occasions. So the answer is yes. And the saving in that case was of the order of 30%, based on day rates of rigs and time saved and costs saved.
Right. Thank you, Mark. There's another one here for you, Mark. Has there been any publication made on the work with the SSTD? Please, I would be interested to read. So
Yes,
if there
and
is,
we
we
do
can
have,
always share that afterwards.
Yes, I'll put my email address there. If anyone's interested in that, let me know and I'll give them a case study.
Fantastic, thank you, Mark. There's we can share that around afterwards as well. There's one here about lifting. Before lifting the structure on its piles, I assume you internally cut the piles just under the mud line. If so, what tool did you use for this? Was it a water jet like the AXE or a mechanical cut? That's for Doug from IQIP.
Yeah, I think Mark is better placed to answer that one, Rhian. Looking down the chat, cutting is outside of our scope, but Mark, I think you responded to that question.
Yes, that's right. And it's usually done with an abrasive cutter. The configuration is slightly different because when we're cutting wellheads, we land out on the wellhead and we cut, somewhere between 5 and 8 meters below the land out because the wellhead is sticking up a few meters. When we're cutting piles, it's a slim bore tool which runs inside the pile. So there's usually a winch that lands out on top of the pile or on the platform. That is able to deploy to a known depth, and then some sort of a centralizer or packer is inflated to locate the cutting tool at the right depth. Sometimes there's a blockage and they put in a soil plug removal tool, which is effectively an airlift dredge goes in. They dredge the inside of the leg so that they can get the cutting tool below the mud line.
Right, thank you, Mark. Simon, WaveX, is the wave energy concept intended for platforms that are decommissioned and left in place rather than fully removed? If so, how is the long-term responsibility for the infrastructure typically allocated between the original petroleum title holder and any new operator using the site?
Excuse me, great question. Yeah, don't think we'd say no to any use, whether it was for a platform that was left in place or whether there was use case for it in the fully removed state. But the best way to think about our approach at the moment is to think of us like another part of equipment that comes with the decommissioned asset, like any other maybe subsea infrastructure that gets allocated with the assets. So yeah, it would go whatever the case is for the rest of the assets. We'd be in sort of like another piece of equipment. But yeah, really open to having a further conversation about that as well. That would be great. Thanks, Maureen.
Great. Thank you, Simon. We have a question for Louise from BMT. Can DEEP be used to plan for decommissioning of offshore wind farms or aquaculture as well as oil and gas platforms?
Yeah, short answer, absolutely. So that's a really good question because we did focus our presentation more on oil and gas. That's where the technology for DEEP came from. But already in terms of an operating space, DEEP has been applied to both aquaculture and offshore wind farms as well. So there's nothing stopping it from doing the same application through for the decommissioning of those. And it's really interesting because we do talk a lot about decommissioning of oil and gas because that's what we've got in Australia. But now when planning new infrastructure in maritime space, decommissioning has to be planned before the feasibility licenses are granted. So that's a really great application, both of those applications. Mm-hmm.
Great, thank you. We had a very nice comment from Shetland. Thank you for the webinar, for all the speakers. Well done, lots of valuable information. Doug, I do have a question for you. Marine growth weight, can you talk to us about what is associated? How much are we talking about with marine growth weight on average? What have you found?
That's a good question as well. That's probably one for the contractors more than us. Typically, we get given a set of load cases to analyze and say, right, okay, the maximum load per tool or for a structure is X with an off-lead angle of X. But in my experience, we could be looking at anywhere between 20 to 30% additional weight, not only on marine growth, but it's also the additional bits and pieces that get welded on through the life cycle of the structure, because something that goes into the field, 20 years ago never comes out looking the same, and there's never drawings to, or rarely are there drawings and good traceability to understand exactly what has been added. So You're exactly on the money, Ryan. It's quite a difficult topic, and to understand really what weight it is that you're dealing with is challenging. And to design equipment that can deal with material that has corroded and has faded, as well as the additional steel that's been added, plus marine growth, is quite a challenge.
Yeah, great. Thanks, Doug. That's phenomenal, 20-30%. I am not seeing any more questions in the chat, so I would like to call it to an end. Thank you, everyone, for joining us for today's webinar, and we'll see you at the next CODA webinar. Thank you very much.